Let's find about the effects of spherical video-based virtual reality implementation on students' natural science learning effectiveness with us.
Virtual reality, VR, has become an important topic of education technology in recent years. Augmented reality and virtual reality are very popular topics in the technological community and in the education field, and the range of their application is also very broad. The experimental group students used the hands-on approach to design an SVVR system to learn natural geomorphological knowledge. The control group used the conventional SVVR guiding system to learn.
Mobile learning has three meanings and values: convenience, expediency and immediacy. It enables students to observe in real learning contexts, and provides digital learning information in the right place and at the right time. The effectiveness of mobile learning. Increase students' learning motivation, make learning process more interesting and enjoyable. Help learners improve their learning achievement.
VR is a virtual world in a three-dimensional space that can provide users with visual simulations and simulations of the other sense such as touch, smell, sound, and taste. This technology can let users feel that they are immersed in an environment where they can observe things in the three-dimensional space without the limitations of time and space. VR can be subdivided into image-based VR and video-based VR. These combine technologies from computer graphics and vision, and create virtual environments from either photographs or video images to help users have an immersive feeling in the VR environment. Hands-on learning initiated by John Dewey's 1938 theory of learning by doing that emphasized the importance of experience in learning process. This approach ensures that learners can design their own projects to create links with the knowledge. Positive of hands-on learning. Students solved more problems correctly and quickly with digital devices, help students improve their learning performance and self-confidence, and learning motivation.
The hands-on design SVVR system learning approach. 1. System structure. EduVenture VR system. Software for designing video-based 360 VR learning experiences. Consists of modules for teachers to edit learning materials adding images and text, students to design VR scenes directly hands-on, displaying VR scenes created by students, a database to store learning materials, student projects, and more. 2. The interface of the design platform system. VR design interface. Students use tablets to design VR projects. Students can create multiple 360 scenes, add learning information to each scene, design questions within the VR experience, preview their projects from a user's perspective. The interface of the VR learning system. VR learning interface. Students use tablets to access VR projects. Students can freely explore the VR environment by turning the tablet. Learning information designed by students appears within the VR scenes. Introduction of the learning activities and learning materials. Learning activities and materials. Introductory video of Yalu National Park shown to both groups before VR learning for context. Learning materials prepared by experienced teachers. Teacher guides students in designing a sample question format title, answer, scene changes, etc. Students design their own VR projects. Control group uses a researcher-developed Yalu VR guidance system.
The experimental group had 25 students, and the control group had 19 students with an average age of 11 years old, are the participants of this research. Learning materials. The teaching curriculum of this study is Unit 3 of Elementary School Science and Technology, Mysteries of the Earth. Experiment process. All of the students watched the course video before completing the pretest questionnaire. The control group students then used the VR guidance system to learn the geography knowledge, while the experimental group used the learning materials prepared by the teacher. Research tools, a learning achievement pre-test and post-test, and the questionnaire of learning motivation, self-efficacy, problem-solving tendency, metacognitive tendency, and cognitive load.
The students who learned with the hands-on design VR system learning approach had significantly higher scores on the short answer questions than the students who learned with the conventional VR. The learning motivation of the experimental group students who used the hands-on VR activities was not better than that of the control group students who used the conventional VR system to learn. The self-efficacy of the experimental group students who used the hands-on VR activities was no better than that of the control group students who used the conventional VR system to learn. The experimental group students who used the hands-on VR activities had a similar problem-solving tendency to that of the control group students learning in the VR surroundings. The experimental group students who used the hands-on VR activities had higher metacognitive tendency than the control group students who learned with the conventional VR system. The students who learned with the different learning approaches did not have different cognitive loads after the learning activity.
The ANCOVA analysis showed no significant difference in learning achievement between the experimental and control groups. However, in analyzing post-test scores with t-tests, students in the experimental group outperformed the control group on short description questions after VR activities. Designing VR projects was challenging for some students due to unfamiliar software, impacting their motivation. To prevent reduced learning willingness, personalized support, and scaffolding are recommended. VR was a learning tool used to increase the student's motivation in the learning activity and to provide a well-organized situational environment for the students to learn.